Good afternoon and welcome everyone also from my side. My name is Jens Dahlmann. I'm Application Specialist at AB SCIEX in Germany. And I would like to continue a little bit the analysis of toxins. We keep a strong focus on biotoxins. That means like toxins produced by natural organisms such as like phytoplankton. However, we are going a little bit to move from the land into the sea, and we are going to speak about marine biotoxins. Biotoxins that can be of concern, for example, if you're a seafood consumer, like myself, for example, eating blue mussels. And in various places of this continent, we have the issue of toxic phytoplankton blooms. We are utilizing our LC-MS technology for the quantitation of these toxins, but also we are utilizing QTRAP for conformation and identification of this toxic cocktail. Let me first start then a bit on the instrumentation side, looking the application parameters. Then we are seeing quickly into the toxins itself, have a look on the international guidelines, European, North American, and Asian regulations, and force us to analyze for those toxins. However, not only on the interest on research, we also have to have our eyes open for new substances, maybe some metabolites of these toxins, and that's why we have point number 3, a little bit beyond the lore, maybe preparing ourselves for upcoming changes of regulations. Then we are going to move from marine water into freshwater, having an eye on cyanobacterial toxins such as microcystins. And then we are also have to focus on drinking water, since drinking water can be contaminated by those toxic cyanobacterial products. The last part is then a little bit on the online monitoring. So we are equipping a marine research vessel with the equipment that allows us for very on-time measurements. If we look at the phytoplankton, I think it becomes obvious that we have to deal that we are dealing with a cocktail of substances. There are various substances on the screen now, like oxalic acid group, the oxalic acid itself, but also we have like different DTX toxins. Major concern is the toxicity that can cause strong diarrhea. That's also where the name comes from. However, nowadays we're also shifting a little bit the vocabulary and calling this group of toxins lipophilic toxins. And as you can see here, like we have DTX 1, 2, and 3, we have the oxalic acid itself. So always in this application field, we want to make a kind of multi-method for these substances. On this side, we see like the pectenotoxins, also belonging into the field of the lipophilic toxins. Maybe even the same organism is producing those toxins, and we are speaking about, for example, PTX1, PTX2, and you can see already from this configuration that the list can be extended. That means we have to be always open for substances with similar structure and maybe similar or even different toxicity. On this side, we see the yesotoxins. Yesotoxins also part of certain regulations, so we have to analyze them on a quantitative scale, the yesotoxin itself, but also structurally related yesotoxins. And once again, we all would like to fit them in one multi-method. And as you can also imagine, when you look at the structures, some of them will ionize nicely in positive mode, while others will do better in the negative polarity. So the instrument should have some capacity for fast polarity switching. The azaspiracids, for example, a relatively new group of substances, for example, produced by Acidinium spinosum, and the structure here on the right side, also kind of slightly bigger molecule, but still something to capture in our application, and hopefully also can fit it into the multi-method. If you look at the different methods that are so far published, there are different type of pH levels, like we have acidic method, alkaline methods, we have neutral methods, and these days, of course, we see a trend from classical HPLC to more ultra high performance liquid chromatography. The method that we are going to promote today is the acidic method. It allows for fast analysis of these compounds. However, we have also successfully implemented the alkaline method and the neutral method on our equipments. If we look at the acidic method, of course, the pH is reflected by the mobile phase. We have an acidified mobile phase with the formic acid. We're adding a little bit of ammonium formate, and the whole method is LC-wise set up on an water acetonitrile gradient. We are utilizing the state-of-the-art Phenomenex core shell technology. A kinetics column, reversed phase type of material is used here, and our exigent expert Ultra LC100 system. The instrument that we are having on the mass spec side on this application can be, for example, the SCIEX QTRAP 4500, 5500 system, but we have also utilized, for example, the 3200 QTRAP version. We have always to focus a little bit on the guideline values, so sensitivity is a critical point and should always be evaluated by selecting the system. What we are also using here is the scheduled MRM algorithm. That means like the acquisition of the analyte based on the retention time with fast polarity switching, and an option if you have the QTRAP version of the equipment is the MS library searching, because we are acquiring full scan spectra. Now let's have a look on the chromatogram, and on this picture you see the fast acidic LC method on the QTRAP 5500 system, and this is done in one run, as you can see, like with positive and negative polarity switching. For example, here the yesotoxin in negative mode, while for example the azaspiracids are nicely ionizing in the positive mode. The whole runtime is 8 minutes. Of course, optional to bring it down a little bit further, but we should not forget the robustness of the method that we need to fulfill here. Baseline separation for some of the compounds may be required because of different toxicity, and we sometimes have to sum up the analytes in order to fulfill the guideline values. This instrumentation that we are here utilizing, the QTRAP 5500 or QTRAP 4500 system with its nice linear ion trap capacity, allows us for even confirm the substances that we are doing in the quantitation mode. We're also having capacity here for further identification aspects, and I would like to show you a few examples here where we combine quantitative work with identification utilizing the QTRAP instrumentation. The QTRAP instrumentation here for marine biotoxins will operate in a kind of MRM survey scan. You have seen the chromatograms already where we are detecting peaks. Once we have detected peaks above a certain intensity threshold, we are automatically triggering our so-called enhanced product ion scan. The enhanced product ion scan on the QTRAP is a fingerprint spectrum that we can use, for example, for library searching. Together with our collaborators, Mike William, for example, in Halifax, who has tremendously helped us with setting up extensive and comprehensive marine biotoxin libraries, allows us for a very smart workflow that does much more than simple quantitation. If we are, for example, looking on the ASA2, and I have said like the law requires us to quantify these substances at the full extent, we are getting an extra full scan spectra of these compounds. As I mentioned, we can utilize these spectra for confirmation, but also these spectra can help us a little bit for identification. For example, in the azaspiracid metabolite work, where we would like to understand structurally related compounds, where we would like to look a little bit deeper in what happens inside of the shellfish, how this substance can be metabolized there. And as you'll see on this slide, the number of azaspiracids is long. Like we are even like exceeding the number 24, mainly methylation, demethylation, hydroxylation, so a kind of cocktail of S-asperacids. So wouldn't it be nice to have a software, for example, like our LightSight software for metabolite identification, and let the software make a kind of predicted MRM run. So based on the parent information, the software will calculate for us a kind of MRM list, Q1 masses and Q3 masses, for example, based on the hydroxylation, methylation that we have seen, and set up a kind of MRM survey scan that we are triggering a kind of full scan spectra collection. So in this example, we have the ASA 11, the ASA 19, which are probably not part of the regulation, but we can just analyze them quantitatively, and also we have the option for qualitative data acquisition. So this is what I have said. We are going a little bit further beyond the lower, and the good thing is the instrumentation does the required quantitative work for us, but we can implement more and more substances here. And as more we see, as more comprehensive the result can be. Now we are moving a little bit from the marine environment into the freshwater, where we have, for example, cyanobacterial toxins. The structure here on this page is, for example, from Microcystis aeruginosa, microcystin, and as you can see at the position 4 and 2 of this cyclic peptide, we have some variability. This variability in amino acid composition again brings us to a kind of cocktail of substances that we should analyze, for example, in drinking water control. So what we have done a very similar method, like a kind of MRM-triggered EPI method with information-dependent acquisition on the QTRAP system. Here on the left side, the microcystin LR, LW, and the brackish water toxin nodularine. I would like to inform you that the LW, for example, indicates the amino acids that we have used. For example, here leucine and arginine. So the amino acids reflect the name of the compounds. What we see on the right side is the spectrum, the fingerprint spectrum again, for confirmation and also for further identification of these substances, because the journey is still not ended. We're still having more and more things to discover and find more and more things in the freshwater environment. And these substances are of high concern because they are hepatotoxic. They are also known as tumor promoters and should be carefully controlled, as I mentioned, for example, in water quality testing. And you can also see, like by just looking at the spectra, there's a tremendous difference. However, there are also some masses which can be used as very nice masses for a precursor ion scan, for example. 135 is a very common fragment for the cyanobacterial metabolite workflow that people have used here. Yeah, and if you want, you can equip the 5500 QTRAP or on this picture the 4000 QTRAP on board of a research vessel. Now the Rocksolid technology allows us to put it on smaller chips like here and do a kind of online monitoring of phytoplankton. This is specifically important for people who are doing a little bit of research on bloom formation, how stable the bloom is, and at what condition, for example, from the nutrients in the sea, the phytoplankton is producing the toxin. Because the interesting story is that it's not always a toxic phytoplankton. It changes based on temperature, phosphate, nitrogen conditions in the water, salinity. So as more we know, and as quicker we get the result, as more we can tell and also discuss bloom formation and maybe give early warnings to shellfish producers. So what has happened, like our collaborator here, like Bernd Krock, they equipped this instrument and went out into the rough North Sea, drove around the Orkney Islands, the coastline here, went a little bit into more sheltered water around Ireland, and collected a lot of data with those type of phytoplankton net filters and samplers, and then quickly extracted the phytoplankton and analyzed it on the 4000 QTRAP instrument. Here, for example, we have a picture of the ASA1 in the seawater column, where we have the different stations that we have seen on the previous slide. And you see it's quite interesting that the pattern is changing, where some stations are completely free of this compound, as I said, based on the environmental conditions, and some stations are having very high level. And I think it's obvious that at those concentrations in the water, in the phytoplankton, the shellfish production should be warned in order to prevent azaspiracids accumulating in the mussels, and later, of course, when we would consume those mussels, we may have a kind of toxic effect, or at least an unwanted effect on the humans or animals eating those mussels. If you want to understand a little bit more the pattern, which analytes, which masses are linked to which phytoplankton and which may be shellfish, we can utilize the marker view software, where we can just make it obvious where there is some grouping by doing our principal component analysis. The good thing is that we have a direct link into the raw data. We can extract the data, we can get the mass information, and we can, of course, utilize the QTRAP here again and get the spectra, start a little bit with spectra interpretation, but this grouping tremendously helps us to understand the environment a bit better than by just collecting the raw data. So marker view software doing principal component analysis for post-data processing, an option a little bit, once again, like in addition to the regulated toxin, maybe on a kind of research level. That brings me to the end to summarize a little bit what we have seen. Various marine biotoxin that we can find around the world in various different locations. We have utilized our LC-MS equipment, the Ultra LC, the QTRAP 4500, 5500 system that we have, by the way, also established in the European Reference Laboratory at the Anagago site there in Vigo in Spain. A tremendous input that we have is from the NRC delivering certified reference material. These standards are not easy to make because the compounds are quite complex, so we can't synthesize them. We are utilizing fresh mussels, for example, or phytoplankton to produce those chemicals. And we are collaborating with them quite nicely in order to supply us with a complete solution here for the LC-MS operation. The columns that we have seen from Phenomenex utilizing the core shell technology on a kinetic style for fast runs, high throughput analysis, and robust operation of our LC system. Software we have seen, we of course utilize the standard analyst software in its newest version, but we also utilize, for example, the iMethod technology, where we have an electronic file ready to use for these marine biotoxin work. So a quick start, no need for tremendous optimization of your LC-MS instrument. We have also seen a little bit on metabolite identification, like light-side software, marker view software for processing the data and doing grouping. So altogether, this entire package enables us to do the marine biotoxin shellfish on our SCIEX equipment. With this, I would like to thank you specifically the collaborators like Philip Hess from the Ifremer in Nantes, who, for example, utilizes the 5500 QTRAP also for metabolite identification, and also the regulatory toxin analysis on a quantitative side. I would also like to say thank you to Bernd Krock, located in Bremerhaven, right on the sea, who has often shown on a yearly basis on his research cruises that LC-MS from SCIEX is suitable also in rough North Sea conditions. And I would like to thank you, Mike William, for supplying us with iMethod technology data and also the reference standards that we are getting together in our application here. I would like to say thank you for your attention. And I hope that you enjoyed this small trip into the marine biotoxin world, and I would like to invite you for browsing on our website. We have plenty of information placed here. We have scientific papers together with our collaborators. And yeah, once again, have a nice afternoon. Don't hesitate from eating shellfish. I think with the control methods in place, it's still a good thing to do and to eat and to enjoy.